I know Kuhn for a long time. At first, he was my student in physics department, and he was the best in the physics department. Then he chosen to move to chemistry, start working with Wang, and right now he's involved in several projects, biophysics, also part of the quantum information which describe the coherence interaction of the quantum system with the environment. Together with Zhang, I work on quantum search. I work on quantum search long time, and then we have our own ideas how to modify Grover search in order to make it more resistible, more resisting against noise. And actually, we run quantum search on several quantum computers which are publicly available. And actually, we run on all of them, which have 5 qubits for. Today, Zhang will present like complete review of our running of quantum search on different computers with the size of the database 5 qubits, and then we compare different hardware, the ones which are better resistant against noise, and then also we modify Grover search a little bit to make it even more resistant to errors. So with this introduction, Zhang, please start.
Yeah. Thank you so much for the detailed introduction. As Professor Korobin said, I'm going to talk about our research on perform the quantum search algorithm on the state-of-art quantum computers. But I think half of my lecture would be just elementary introduction about quantum computing. I will pose during the lecture, and if you have any questions, just feel free to ask me. I will try to answer them. So this is the outline. So I will first give some basic introduction and also give some lecture about the quantum search algorithm. And next, I will talk about our strategy to improve the quantum search algorithm. And at last, I will show that what's the most recent results on perform the quantum search algorithm on real quantum computers, on different quantum computers given by different companies. So I think nowadays everyone knows quantum computing, and as just the one basic reason is that the quantum algorithm is very powerful, and the reason why it's powerful is called quantum superposition. It's kind of a magic box in the quantum mechanics. Quantum superposition says that different quantum states can exist simultaneously. So you can say this is a typical superposition of quantum states, and this precise state is a superposition of 0 and 1, and you can somehow manipulate 0 and 1 together. So this is the reason why this kind of property is powerful for quantum algorithm, because you can parallelism manipulate different states at the same time. And just this is a brief reason why quantum algorithm is powerful. So just the basic knowledge about quantum computation. The building block is called the qubits. It's the quantum bit. So different with the classically you have 0 and 1, but in quantum case you have a superposition of 0 and 1. And operations on the qubits is called quantum gates. So the only constraint for the quantum gates is they have to be unitary, because this is given by the quantum mechanics. Otherwise, you can choose any unitary matrix acting on the states. You will get different results. This is only rule required by the quantum computation. And for real quantum computers, because you cannot design any unitary matrix, you have to design some basic elementary operations, and you use that elementary operations to construct any unitary matrix you want to perform on the state. So this elementary usually is only single or 2 qubit gates. So this is really basic operation on quantum computers. This is called the universal quantum gate set. Another special point about quantum computation is the nature of quantum computation is probabilistic. So every time you need to measure the states after the computation, and the probability you're getting 0 or 1 will depend on the amplitude before the state. Yeah, as I said before, the superposition is powerful because the exponential scale. So for example, if you have 2 qubits, the basis is, there are 4 bases, 0, 0, 0, 1, 1, 0, and 1, 1. But if you have n qubits, the number of basis vector is exponentially scale. So when you have maybe 100 qubits, the number of bases is already larger than the number of atoms in the universe. So this is very powerful scale of the qubits. So when you have 100 qubits, you already can do a very powerful algorithm. But there is kind of constraint on the quantum computation, because basically, just physically, we cannot say the quantum states. If you have a superposition state, you cannot say that state. You have to do something measure, and you have to change the state into a classical output. So the process is, first you have some classical inputs, and you process this kind of input by quantum evolution. And at the final point, you still need to change this quantum state into classical output. So not everything. So if you have a superposition of the quantum states, that's the basis vector is very large, but you cannot really say the amplitude of different states simultaneously. You have to measure the state and get some classical output. Yeah, but it seems like you can take advantage of the quantum superposition and to design very powerful quantum algorithm. But in general, this is a difficult task, a difficult problem, because as I mentioned, that's the tensions between the classical and the quantum. You have to output classical data to solve the problem efficiently, and there are only few, not many well-designed quantum algorithm that is believed to be more powerful than a classical case. I think the first algorithm, but maybe not many people heard about it, is Deutsch Algorithm. It's a toy model. It's proposed in 1980, around 1980s, a very long time ago. But this is really the first algorithm. This is a toy model. It does not solve practical problems. But after Shor's result, Shor's achievement, that he designs a factor or quantum Fourier transform to factor the integers, which is exponential speed up compared to the classical algorithm. And after Shor's algorithm, this is really the starting point of the quantum computation. And later, just 1 year later, Grover found a search algorithm, which is quadratic speedup. I will talk about this algorithm in details. And this algorithm has a generalization. It's called amplitude amplification. So this is really beyond search problem. You can just amplitude the state you want by this quadratic speedup. So it has huge application beyond the search problem. The fourth point is, if you are familiar with classical random walk, it's a quite good platform to design different algorithms. And for quantum work, it's also demonstrated that the walking speed given by the quantum evolution is faster compared to the classical case. This is another category of the quantum algorithm. And the last one is the most natural one. Is you can simulate the quantum system by a quantum computer easily compared to the classical case, because the nature of quantum mechanics. So right now, during the last maybe 10 or last 10 years, that quantum computers are super fast developed. And also many companies are pretty generous right now. They provide quantum computers free to researchers. So anyone can apply, for example, the IBM quantum computer. You can just register account and the quantum computers online. But if you want to get access to the best quantum computer, probably you still need some kind of funding information. So right now, IBM has the largest quantum computer given by 127 qubits. And this quantum computer is based on superconducting qubits. And also Regate also built the superconducting quantum computers, and the maximum right now is 32 qubits. And a different platform is given by Honeywell and IonQ. Both Honeywell and IonQ, they are trapped ion quantum computers. They have much more, they have better control of the qubits, but the problem is the scale. It's not easy to build maybe 100 trapped ions quantum computers. Right now, Honeywell has 12 qubits quantum computer, and IonQ has 21 qubits. And yeah, as I know that you can, if you are just doing research in the university, you can apply all these companies for quantum computing for free. And if you want to use the best quantum computers provided by these companies, you need to pay somehow. Yeah, but for example, IonQ is pretty cheap. I think every research group can afford to pay the IonQ and IBM quantum computer. So next I will move on to the.
Maybe here I want to make a brief remark. Maybe you should mention IBM, Microsoft, because Microsoft generously help us to use this trapped ion. So Microsoft.
Yeah.
Good.
Just for example, Amazon and Microsoft, they built a software platform. You can apply the Microsoft and the Amazon account. It's called Azure, and you can
right.
Yeah, you can apply their accounts, and they give you some free credits, and through their accounts you can play the IonQ and Honeywell quantum computers, and I think everyone can apply. Is at the early stage, this company are really generous to the public. So next, I'm going to move to the search problem that is also called the Grover search. So the general problem of the search is given by first this concept is called oracle, and given by if you can evaluate this function easily, it means that you can check every state or every list in the database to see whether this input is the target state we want to find. So the problem is find the target state that gives the function value 1, and so you can see if you are looking in this database and the number of atoms is 2 to the n. So the best way for the classical search, if you only have this one function and you do not have other information about this oracle, the best way is you just look in the atoms one by one. So in the computer science, the complexity, it means like what is the scaling of number of oracle in terms of the problem size. It means when you increase the number of capital N, what's the number of oracle you need to solve the problem. So in classical case, this is really nothing you can do. You just look in the atoms one by one. So the complexity is the capital N here. Yeah, but the Grover search is a quadratic speedup, is square root n. So if you have 100 atoms in the worst case, you need to apply the oracle 199 times. But for the Grover search, this is really quadratic speedup, and maybe you just around less than 10 oracles, you can solve the problem. So quantum computing is always taking advantage of the superposition. So the starting point is to create a superposition of all the atoms in the database. So given by this fundamental 1 qubit operation. This is called Hadamard gate. So you can see the Hadamard gate acting on the basic 0 state and gives the superposition of 0, 1. But if you have many 0 state and you're acting on many Hadamard gate, you will have a superposition of 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, and all the superposition of the basis vector in the database. So this is the initial state of the Grover search. And this is some kind of notation to explain why the Grover's algorithm works. You just divide the state into the basis states, the target state and the non-target state. And you renormalize this state, and you can, this should be SN, this is the notation. So the initial state can be written into a target state plus the non-target state, and the amplitude before the target state is sine theta, and theta is given by this this formula. So this state is the same as this one. You just rewrite the states and divide the state into target and non-target state. This is just mathematical tricks to rewrite the initial state. So the next step is, so for quantum computing, for quantum computation, the oracle, you need to change the oracle into the quantum oracle. And because quantum computing are unitary matrix, and the oracle, you need to change the oracle from the irreversible function to the reversible function. And the oracle is designed in this way. The input is x, and you output the fx to this ancillary qubits. So you can say this is a reversible operation.
I mean, for formality's sake, you should say like addition in the circle is addition modulo 2, okay?
Yeah, just modulo 2, and this is y is 0 or 1, and this plus is modulo 2.
And f is also 0 and 1, so take 1 bit plus another bit modulo 2. This is still bit, and bit labeled the basis, orthonormal basis in the quantum space. Sorry for interruption.
Yeah, no problem. Yeah, so this if x is t, so this is given by 1, and 1 if y is 0, you change the 0 state to the 1 state. And another trick is that if this y is a superposition state, if you change the y into 0 - 1 superposition state, you can say that acting the oracle on this state, you will give a negative phase on the target state.
Cool. Maybe it's appropriate here to make a historical remark, because this was discovered by Deutsch, this prehistorical, 1980. And Deutsch, by the way, he's British also. He's from Great Britain. Okay, sorry for interruption. Please continue.
Yeah. This trick is firstly designed in the Deutsch algorithm, which is the first algorithm in 1980s. But later this trick is applied to many other different algorithms, also applied in the quantum search algorithm here. And so you can design the oracle instead of in this way, just design the oracle acting on this superposition of the ancillary qubits, and you will give a negative phase of the target state. So if this if this x is t, so you will give a negative -1 phase of the state. So you can just simplify the notation as of this oracle. Let's give a reflection in terms of the target state. So this is how the oracle applied in the Grover search algorithm to give a negative sign of the target state. But as you can see, if you only have the oracle, you cannot solve the problem, because when you change the sign of the amplitude of the target state, you do not increase the amplitude of the target state, and therefore after doing some measurement, you still cannot find the target state. So to solve this problem in Grover's algorithm, Grover introduced another operation. It's called diffusion operator. This operator is reflecting the average of the amplitude in the database is a little bit abstract. Yeah, I will later give example to say. So this is the initial state defined before.
Maybe
So
maybe notations. So here D first is identical matrix -2, and
yeah.
the second one the projector on this vector SN is the total average with respect to all items into that database. This is Dirac notation. So I don't know if everybody familiar with this notation. So this the
Yeah.
second term is SS. This is a projector to one vector, which is SN, which was described above. Sorry for interruption. Please continue.
Yeah, no problem. Yeah, this is exactly the projector. This brackets notation in quantum mechanics, and you're projecting the state onto the SN state. But you can, for quantum operations, this is unitary matrix. So you can design the projector in this way, -2, and this is unitary operation, and this is a valid quantum operations, and it's reflecting the amplitudes around the average. So combine the this is the oracle, and this is the diffusion operators. Combine these two operations. This is so-called Grover operator or Grover iteration, and they have different name. And this is the element in the Grover's algorithm. So the Grover algorithm is simply apply this operator on the initial state many times. So you just apply maybe j times of this operator on the initial state. So the magically is that, for example, the initial state is this red vector, and you at the beginning, if you can rewrite the target state and the non-target state as sine theta plus cosine theta. After you're applying this Grover operator, you can see this operator is really a rotation in two-dimensional space. So applying this operator j times, you just rotate the initial state to the target state. And it means that after applying the Grover operation on the initial state, the amplitude or the probability of finding the target state is amplified. And this is a geometric picture that you're reflecting the initial state to the target state. So this is a mathematical formula that you apply the Grover operator j times on the initial state, and the amplitude before the target state will amplify according by this equation. If you want to find the target state with probability equal to 1, so this has to be 1, right? So this j has to follow this formula when this 2j plus 1 times theta equals pi over 2, sine pi over 2 is 1. So you will find the target state with almost 100% probability. And the optimal number of iterations.
You have this equation with pi by 2 in the left-hand side. 2j, j should not have a subindex 1, right? 2j plus 1.
Yeah. This is another, typo here. Yeah, this is 2j plus 1, same j here. And this is the optimal number of iterations in the Grover search. So you can see this is a quadratic speedup. You only need the square root n of number of oracles to find the target state with 100 probabilities. So this is Grover algorithm. Yeah, maybe just a quick remarks that also Grover algorithm can find multiple target search algorithm, but the number of iterations should be changed. So we need to know the number of target items in the database before we run the search algorithm. Also, Grover's algorithm is optimal in the number of oracles. You really cannot increase the complexity, the oracle complexity of the Grover search algorithm. So as you can see, Grover algorithm is some people would say it's more like invert the function instead of search. If you have this one-word function, you want to find the solution of this one-way function, you always can apply the Grover algorithm in this way. And by this idea, the generalization of Grover search algorithm is called amplitude amplification. Yeah, this all what I want to say about Grover's yeah, just
can I say something? So this last remark by Kuhn that Grover is more like inversion is kind of important because one can try to use Grover to break encoding, and that's one of the uses. Anyway, this is the end of the first half of the lecture of Kuhn Zhang. This was like, in our mind, this was general introduction. Later we'll go into the detailed description of our modification of Grover and, the results of running on the specific hardware. So, if there's general questions about general quantum information, Kuhn, you can take from here. I finish with my comment.
Yeah, sure. Yeah, the comments. Yeah. So Grover search algorithm is really the standard for the encryption. That's if there nowadays it's called post-quantum encryption standard. That's if the encryption cannot be solved by the Grover's algorithm, it would be safe in the post-quantum era. And many research already designed the oracle to decryption of the code. So this is application of the Grover search. It's really searching the code of the problem. Yeah.
I guess you should continue, Kun. Just continue.
Yeah. Just so for our work, let's so nowadays people call the number of logic qubits is called width of the algorithm, and the number of quantum gates is called depth. But in order to perform any algorithm, you have to change the abstract operations into this single and two qubit gates, this universal gate set. And right now, what's the problem is not the number of qubits. We already have many qubits, but it's depth. We really cannot apply many operations on the qubit. So what limits the power of near-term quantum device is really the depth, not the number of qubits. So Grover algorithm is optimal in the number of oracle, but the question is, can we improve its performance on the real devices? The answer is simply yes, because the oracle is not the only operation in Grover's algorithm. So the next step is in our research is that we just rescale, renormalize the diffusion operator in this way. So you can see the diffusion operator only acting on a subspace of the database. And accordingly, we define this called local Grover operator. And this is the local diffusion operators. So if I'm smaller than n, this operator is more easily realized on quantum computers because this operation is only acting on the subspace of the database. And yeah, this is one diagram. So this is oracle. UT is some kind of abstract function, and this is diffusion operators. So this is a global diffusion operators, and this is Hadamard gate. This is Pauli X gate, and this is the n-qubit Toffoli gate. If you just rescale the diffusion operators into a subspace, and this is what we define the local Grover operator. So yeah, this is one of my favorite diagrams. So before I show you that the Grover algorithm is really a two-dimensional rotation from the initial state to the target state. Yeah, but when you have the local diffusion operators, it really becomes a higher dimensional rotation. That's from the initial state. You want to rotate this initial state to the target state. When you have more diffusion operators, more different kind of diffusion operators, you will generalize this rotation into higher dimension. So the best way is find the short path from the right vector to the target state. Yeah, based on the local diffusion operator, we have three strategies to lower the depth of the quantum search algorithm. Yeah, the first one is just straightforward because you have local diffusion operators. So you only search local space, and for the rest of the qubits, you just random guess what's the target state. So you renormalize the search algorithm by these local diffusion operators. And the second one is more complicated, and you use this partial diffusion operators. Just second one is using this diagram. Let's say you use local diffusion operator to find the path in this three-dimensional rotations, and but the path is found given by the lowest depths of the operations. The third one is called divided and conquer. You can really use the local diffusion operator to find only part of the target state, and you reinitialize the initial state again and find the rest of target state. So just a few remarks, and so if you reduce the depths of the circuit, you will reduce the noises. You will increase the success probability on the near-term quantum computers. What we talked the strategies before, we can jointly apply together. But for different problems, you have different oracles, and for different quantum devices, you have different connectivity of the qubits, and for different quantum devices, you have different error rates. They really have different optimal search circuits. So you really have different ways to perform search algorithm on different devices. Just one last remark is that you can say the divide and conquer is really another way to parallel the quantum search algorithm on different quantum computers. So just the next, I will give just the example. It's kind of straightforward. So this is the 5-qubit search algorithm. So this is the initial state, and you apply the Hadamard gate to create the superposition. And next, you apply the oracle, and this is the 5-qubit diffusion operators. And given by this circuit, after measuring the qubits, the success probability finding the target state is given by this number. So you can say you only need one oracle. You already can find the targets, the target states around 1/4. But there are 32 32 items in the database. So this is really larger than the classical case. For this one, is you apply 2 Grover operators. You can say you just repeat the oracle diffusion and oracle diffusion, and then you can say the probability increased from 0.25 to 0.6. And also you can say that the probability does not increase in a linear way. When you have 2 oracles, you even double the success probability. This is one difference compared to the classical search. So the next, if you have the local diffusion operators, you can really renormalize the search space, and you can see you only create the superposition in these 3 qubits, and for the rest of the 2 qubits, you just random guess, and given by our, but you cannot renormalize the oracle because there's nothing you can do to change the oracle. If you change the oracle, you change the problem. So you only can renormalize diffusion operators, and in this way, you random guess 2 qubits and performs the renormalized search on 3 qubits.
The powers of X, the I capital sub 1 and I capital sub 2, it's a bit, right? 0, 1, correct?
Yeah, it's L1 and L2 is 0 or 1. It means you random guess the target state is 0 or 1. If this is 0, it means you just guess that the target state at here is 0. And if you guess this is 1, you just change this 0 state to 1 state, and you random guess this is 1. The target state is 1 here. So similar, you can renormalize. This is another just a renormalized search space into only 2 qubits. Similar, this is a random guess of the target state. This is divided and conquer. It's a little bit more complicated. So at the first stage, you only find, you can say you only measure these 2 qubits, you only apply diffusion into these 2 qubits. So you really only amplify the target state at least 2 qubits. And after measure these 2 qubits, and you reinitialize the states based on the measured results, and later you find the rest 3 bits of the search domain, and you can see this is this is really divide the search algorithm into 2 steps. The first step you find 2 qubits, and the next step is you find 3 qubits. The success probability here is 0.26. But if you change you have the exactly same operation, but you only change the order of the diffusion operators. You can say the first stage you find 3 qubits, and the second stage you find 2 qubits. The operation is exactly the same as before, but the success probability is different. The reason is
maybe you should mention that 2 qubits. We should have in mind that exact address of the target item. That's the item which we're trying to find. The sequence of 5 bits, and then here you first find first 3 and then second 2. So it's like sequential, right? You agree, Kun?
Yeah. Just all the examples here, you can say we want to apply at least 5 qubit search algorithm.
Just some pedagogical remark. Please continue. Sorry for interruption. Please continue.
No problem. So in this sequence, you find the 2 qubits in this first algorithm, and in the second part, you find the rest 3 qubits of the target state. But in this way, in the first sequence, you find the 3 qubits in the first stage, but for the second one, you find the rest 2 qubits. When you change the order, it really changes the success probability here. Although the operations are exactly the same, only the order are different. So given by this example, so anyone have question or comments?
Do you have any insight as to why that reordering, doing 3 versus 2, and then or the other way around, why one gives that higher probability? Why is that?
You mean why this one gives a higher success probability, right? Yeah, right. Because just the intuitive understanding is that at the first stage, you really want to apply the large diffusion operators, because in this way you amplify the amplitudes more efficiently in the first stage. Because in the first stage there are so many atoms in the database. So when you apply large diffusion operators, you amplify the amplitudes more efficiently. So that's sort of intuitive understanding why this order is better. Yeah.
Can I say something?
Yeah, sure.
Robert, our philosophy is different. I mean, nowadays quantum algorithms measures of the old Oracle complexity is kind of outdated. So what we're trying to say right now, there's several different characteristics of how algorithms runs of hardware, and then right now our main point is to reduce the depth, meaning that use less of the 2 qubit gates, and then this will reduce noise. So our modification of Grover is not so much increasing probability, it's mainly decreasing the depth. So less gates, less noise. That's our philosophy.
Understood. Nice.
Yeah.
Thank you.
Yeah, this is yeah, if no questions, yeah, I will show the real results on real machines, on different machines. So the setup is for the 5 qubit search algorithm, and the circuit are these examples shown here. And so this is search algorithm of the target state among 32 atoms in the database. So first you need to choose oracle, but different problems have different oracle. We just construct a toy oracle which finds the target state as 01011.
Can I make a stupid remark here?
Sure.
Kind of in the real machine, it's really important that we choose that one, because usually the machine initialized in 000 is a ground state, so machine will go by itself to the 000. So if the target state is 00, you don't need anything, any algorithm. It will just machine will fall down to 00 by itself. So it's important that we chosen some non-trivial address because of the engineering problems of the machine. Sorry for interruption. Please continue.
Yeah, that's good comments. Yeah, because if you really have a bias on the target state, if you, for example, you choose the 0000 state, it really has a higher probability, naturally has a higher probability compared to other state. So so to exclude this bias, we just random choose this target state. So in order to get the probability, you need to run the circuit many times. So this is the times, this is so-called shots of the circuit. So you run the circuit 400 shots, and you can get a distribution of the output. And we run 400 shots 3 times to estimate the variance of the distribution. Just one remark, like there's always a trade-off. It means when you have more qubits, you always can reduce the depth. Reversion is also true. When you have less qubits, you always need to increase the depth. Yeah, but as I mentioned before, that really the depth is the limitation in the near-term quantum computers. So we choose the least depth to perform this circuit, but we need 1/3 qubits for the 5-qubit search algorithm. So in our example, there will be 6 qubits, but 1 qubit is the ancillary. This is just a remark.
And sorry to interrupt that.
Sure.
How long does it take to run these experiments? So 400 shots, how long does that take?
You mean just the real time?
Yeah, real time. You're sitting at your keyboard. How long does it take?
When you submit the job, you need to wait because there's a lot, and the waiting time. The waiting time is really
Okay.
The waiting time is really fluctuating. But the actual time is just less than maybe around seconds to run the circuit 100 times, because this is really super fast operations. But the waiting time is, yeah, sometimes when the machine is offline, you really need to wait several days.
Yeah, waiting time is several days.
Okay, thank you.
Yeah, no problem. So just the metric to benchmark the result. The first one is success probability finding the target state. This is natural. But the second one is what we call is the expected depth. It's the circuit depth over the success probability. So this metric means that what is the average depth you need to find the target state. So this is renormalize the depth according to the success probability. Yeah, but there are more metrics, but I'm not going to show here, such as selectivity and the circuit fidelity to benchmark the deviation of the output from the theoretical distribution. So this is the result from real machines that we get in last month. This is the latest result. So first, the black line, the black dot line is the theoretical value, theoretical success probability. And you can see 4 colors. So these two, the blue and the yellow, are from IBM quantum computers. And this is the name of the machine. It's called Lagos and Mumbai. And so these two from IBM. And the green one is from IonQ. They have the trapped ion. They have 12 trapped ion quantum computers. And the orange one is also trapped ion quantum computer from Honeywell. Yeah, they changed the name nowadays. They changed the name to Quantum Womb.
Oh, maybe we should ask Robert. The Honeywell right now changed the name Quantum and just to use Quantum. Is this like some Latin? I mean, this is like a British company. I mean, is there some foundation in English language to insert the second U in the Quantum?
I think they're playing with words to get a good trademark.
Okay, thank you.
I think they're playing with the word vacuum. as well.
Yeah.
Okay. Kun, please continue.
Yeah, sure. Just just Honeywell changed the name already. I think starting from last month.
And this is the best, right? It's clearly the Honeywell is like superior to all others from this.
Yeah. So just a little bit more information. So for example, for IBMQ Mumbai quantum computers, they have 27 qubits. But for the Honeywell, they only have 12 qubits. But you really don't need that much qubits to run some algorithm. You can say that's but for Legos, they only have 7 qubits, and the Legos and the Mumbai have similar output, similar results. But Honeywell is really the best. They have the best fidelity. They have the best output distribution, and the output is really close to the theoretical value for all the circuits. And also for different circuits, analyze is here. So this one is Grover. This one is Grover. But we changed the algorithm just to reduce the depth, also reduce and also decrease, lower the success probability. But you can say that for this circuit, this is really short circuit. So you can say that the IBM quantum computers has higher success probability compared to the Grover search. And this is divided and conquer way. And for this divided and conquer, it's really not efficient as in this way. And the success probability for this divided and conquer is higher compared to this one. This is I think this is one of the most important results we get last month. To give you some kind of impression. Right now, 5 qubits is really the borderline. You really can't run 6 qubits or even higher. This is really what we can do best right now. And among the different quantum computers, Honeywell is really good. But the bad news is Honeywell is really, really expensive. Maybe you need $100,000 for 1 month for some credits. They're really expensive, but they really build some good machines right now.
So Kun, are you going to discuss selectivity and depth? Yes, please.
Yeah, just
it's important.
The depth is another metrics to the expected depth is the average depth you needed to find the target state. So you can clearly say that the original Grover search is really not that efficient when the system.
So to interrupt, just for our understanding, the first one was probability of success, which we want to be large, right? But this expected that we want it to be low. So the fact that Honeywell is low, it's good. There's less noise. So we do want our main purpose was to reduce the depth, and that's it's clearly achieved on Honeywell. Sorry for interruption. Please continue.
Yeah, that's right. You really want to decrease the expected depth. This is also you can understand as expected running time to find the target state, because more depth means more longer running time.
Maybe I may make another interruption. I apologize. So reducing the depth, meaning that I reduce the number of times which I use 2-qubit gates, and the 2-qubit gates is a physical device. So the usage of this 2-qubit gate takes some time, some microseconds, some fixed number of times. So if I reduce the depth, the number of 2-qubit gates, it's actually reduce the number of physical time on the clock of running this quantum algorithm.
Yeah.
Want to make a comment. So please continue. Sorry for interruption.
Yeah, so you can understand this is as expected running time to find the target state. And Grover is because Grover has longer depth, so it becomes less efficient compared to you just reduce the depth and to magnify the result here.
Quick question, Cohen.
Sure.
So what is the connectivity of Honeywell looks like compared to, like, let's say IonQ or the IBM machines?
Right now Honeywell and IonQ they open to the public of 12 qubits, and the 12 qubits are all connected.
Fully connected graph. It's fully connected.
Yeah.
Oh, I see. So it's like it's not like a circular or anything. It's just everything is connected to everything.
Right. Any pair connected. So it's like really good.
Yeah. So
Okay,
this is
in my opinion.
Yeah, this is really difficult because you have 12 qubits. You have connected all the. You can apply the 2-qubit gates on any pair of 2 qubits. But in future, it's very unlikely if you have hundreds of trapped ions.
Right.
You can have maybe you can have 20 connectivity for each qubit, but our connectivity only limited to maybe 12, maybe 20 qubits.
Is the operation, I'm sorry to interrupt, but it's very interesting. So how does the operation time vary for these? I would imagine for the trapped ions, the time for an operation, a 2-qubit gate.
10 to the minus 3, 10 to the minus 3 second. 10 to the minus 3 is a 2-qubit gate on ion trap.
Whereas on the solid state devices, it would be
I think it's larger, but I don't remember the number.
Microseconds, presumably,
Yes.
on the IBM.
In general, I read other papers that in general, operation of trapped ion takes longer time than operating the superconducting qubits. But somehow measurements, the time of the measurements on superconducting is longer than the trapped ion. Yeah, but I right now I really don't know the exact numbers because I don't find a report on the running time of the different devices.
Yeah, it's difficult to find running time. Somehow it's hidden somewhere.
One more related question. So as you've mentioned a couple of times, it's sometimes possible to trade width for depth. So would that be possible here too? So on that IBM machine with 127 bits, could you use those 127 and offset that additional depth?
Yeah, in general, you want to treat the width to depth, but there is a border. There's a limited. You really can't decrease the depth anymore because the connectivity of for example, the IBM quantum computers, each qubit only connected 3 qubits at most. So you really cannot do much to increase the number of qubits to reduce the depth.
But does that mean that IonQ could do that better because the connectivity, everything is connected to everything, so you could like substitute, trade off like that depth with the width?
Yeah, IonQ really can do more about this trade-off. And also, I can show you like here, you can see the expected running time on the trapped ion system. This is theoretical value. So this is theoretical value lower than the superconducting qubits because the connectivity. You do not need you will need less operations on these fully connected qubits. This is the theoretical value, and also there is in trapped ion you can increase the depth and yeah, but in our case we only use 1 acellular qubits. We didn't. Yeah.
Can I say something? My education was in physics, so maybe I should emphasize the point of view to physicists or of physicists to this. Well, superconducting qubit is large, it's macroscopical. You can take it into your hand. So it means more atoms, more noise. On the other hand, trapped ion is just one atom without an electron. So it's like under control of quantum optics. We call this AMO, atom molecular optics. And then what I'm trying to say, but that by physics, trapped ions less noisy than superconducting qubits. That's what I want to pronunciate. That's all. Kun, please continue.
Yeah, sure. Just if no comments, I will continue. Let's the expected depth. This is the amplified zoom in of this diagram. So you can see even for IonQ, you can design the quantum search algorithm, which gives lower expected depth compared to the Grover search. So this first two is really Grover search, and this the rest of 4 circuits are our new designed search algorithm. And so even though the success probability decreased a little bit, but the price is to minimize the expected depth of the search algorithm. And this strategy can be applied to all the machines, and this is the results here. Maybe I will just quick one. Because we want to benchmark the results by some simulation, and this diagram means like the horizontal line is the simulation of the arrows. So this epsilon is when you have large value of large arrows, you can see the success probability will decrease, and the color dots are result from the real machines. So you can see that the error rates for the Honeywell is really good. It's below 10 to the negative third. So Honeywell is the best among the other machines. And but another way to look at the diagram is like, so you can see different algorithms will have different curves. And for the circuit with the partial diffusion operators, you can see we really can just flatten the curve. So the curve will not become, for in this way, this is a Grover 2 iteration. You can see the curve is really steep, right? You can just change it. And so in this way, it means that for this circuit, they have a better noisy resilience to the noise, and this is some noisy simulation to benchmark the real results. So maybe just quick conclusions. Let's so first, the Grover algorithm is optimal in the theoretical computer complexity, but in real machines, you can really improve the Grover's algorithm. But for this is for future research, because when you have maybe 50 qubits, and how to design the optimal circuit depth is really non-trivial, because the different operations are not commute, and we do not know the general structure for design the optimal search algorithm yet. We are working on in this way, and also for our implementation on real machines. Right now, the machine really can only afford 5 qubit search algorithm. This is really the best they can do. And also, as you can see the news, also from the report, that, for example, IBM already have 127 qubits, but there is really nothing much you can do about these 100 qubits machines to do some practical circuits, practical quantum algorithm. But it's so I think that's the reason why Honeywell is really good, because they have good quality of the qubits, although they do not have much qubits for their machines. So in the next, so right now the research following the quantum algorithm is people are trying to design other algorithm to give some resilience to the noises. So you can so in the future they can use these noisy machines to find some practical value of the quantum computers. This is conclusion. So basically the talk is based on our these 3 papers, and this is theoretical one, and the rest 2 is experimental one. So this, just acknowledgement. Thanks, Professor, and thanks the co-author, and we also acknowledge the use of the IBM, IonQ, and Honeywell. So just I'm happy to answer any question or comments.
Yeah, thank you very much.
Yeah, thank you.
Appreciate it. That's great. So in these search algorithms, you always need this oracle, right? And I hear the word oracle, it makes me think of Greek mythology, and in a real world search problem, what would an oracle be? Would it have to be like a quantum memory or something that doesn't really exist now, or is there an oracle that could conceivably store a database of some complexity?
So just for real application, like the Oracle, yes, for search is somehow it's not a good name. But I would say like just for quantum oracle, you need some quantum operation to realize this one-way function. For example, this one-way function could be a password check. Yeah, so you can construct operation to check the password, and you change this function to the reversible computation, and next you change the reversible computation into unitary matrix, and you can apply this function on quantum computers, and this is really the oracle they can realize on real machines.
Okay.
Yeah.
Robert, can I say my philosophy about Oracle?
Oh yeah, yeah.
You know, in my view, this search of the database which we do is kind of similar to cryptography, because in cryptography is all cryptography based on one-way function. So it's easy to encode the message, but difficult to decode it. So it's easy to calculate direct function, but inverse is a headache. And then this Oracle, that's what it does. I mean, like, cryptography exists in real life, so it's possible to decode, to encode in such a way that it's difficult to decode. So I don't know. I understand this is philosophical, but that's how it's built into my mind. Sorry for it. Yes, please.
Yeah, because I saw other papers, they construct the quantum oracle from the reversible computation. If you have a one-way function that is reversible, and you can just change it into the quantum oracle. Yeah, but different problems will have different oracles. It's really flexible. Yeah, but also this is a research topic, because for different problems, for different NP hard problems, how to construct the oracle, how to efficiently construct the oracle, is still I don't know the general answer to construct the general oracle for the NP hard problem. Yeah.
Okay. And coming back to that 127 qubit IBM machine, is it even possible to entangle all of those bits simultaneously with the available?
Yeah, of course not.
Okay.
I think the record for now to entangle all the qubits is around 30 or yeah, really you cannot entangle all the qubits. It's really too much. Yeah.
Well, there don't seem to be any other questions from the audience. So before we wrap up, let me draw your attention to the very complimentary comments in the chat window. So you should have a look at that. And there's a comment from John Longton, who, if you don't know, is the Dean from the College of Engineering and Applied Sciences. And he thanks you very much.
Yeah, I saw the comment.
Maybe his great remarks, so thank you very much, Robert. Can I say something else?
Yeah, absolutely, yeah.
Also, maybe I should say that in China, in continental China, they have their own efforts to build quantum computer. The last one, which I know from the news, called Chapter 9. And Chapter 9, I mean, this is like historical knowledge in the ancient China 2000 years ago. There was some book about mathematics, which was called Chapter 9. And right now, the Chinese have their own quantum computer hardware really working, which is comparable to the ones which were mentioned, but it's not publicly available. That's all what I want to say.
Yeah, just unfortunately, every quantum computer in China is not open to public. Yeah.
Okay.
Well, very good. Thank you very much again. And
thank you for inviting us. Thank you.
Yeah. Thank you for everyone.
And for your comments, Robert. We appreciate your comments. Thank you very much.
No, thank you. We can bye.
Okay, bye.
Thank you.
Okay. Yeah. Bye.